Howdy kids, this is your video on simple harmonic motion, or why Miley Cyrus doesn't matter, and we're going to find out why she doesn't matter in a second. So, question: what do springs, a wrecking ball, and a guitar string have in common? I'm going to let you sit there and think about it for a while. You probably can't think of anything, but the answer is simple harmonic motion. Simple harmonic motion is any periodic, which means repeating motion that is from a restoring force. So a spring is going to have periodic motion because it will happen over and over and over and over until infinity, until the world explodes. The spring will continue on, and we call that periodic, meaning that it will continue over and over and over. This would be repeating. Now obviously this is an ideal spring, and so it will continue repeating on to infinity, but not every spring would. And that's why a wrecking ball would be considered simple harmonic motion, because a pendulum, something that is being pulled by gravity towards the center on a string, would be considered simple harmonic motion because it's repeating. And a string on a guitar or a violin is considered simple harmonic motion because, as you can notice, the string is moving back and forth, and so that is a repeating motion that is occurring multiple times over and over and over again from a restoring force, which would be the tension in the string. So think about this example. The moon going around the Earth is periodic, as in it repeats. It happens over and over and over every month. The moon revolves around the Earth. And so, is this considered simple harmonic motion? And the answer is no, it is not. Because at any point, so gravity is not trying to restore the moon to any one position. The gravity is just pulling it into a circular path. If gravity turns off, then the moon does not continue in a circular orbit. It will just continue off into space forever to die. So anything that is rotational is not considered simple harmonic motion. So first, we're really going to look at only two examples of simple harmonic motion in this level of physics, and that would be springs and pendulums. So springs have something to do with Hooke's law. And so first we have to establish some terminology. So if this is a spring attached to some sort of mass and it is moving back and forth, okay, the center point where we started from, let's say we started from somewhere and we stretched the spring a little bit, that center point is called equilibrium, because that's where it wants to kind of be, but it's never really able to achieve that. And it stretches a certain positive distance away from equilibrium and a certain negative distance away from equilibrium, and we call that maximum displacement. And another word we might use is amplitude. Because this is starting the waves unit, we're going to see that amplitude has something to do with waves too later. Okay, so let's pause it and freeze it right here. At this one moment in time, there is a force on the spring, and the force is attempting to bring it back to equilibrium. And so the force is going, notice that the force is going against what X is. So X is being stretched this way, and the force is pulling it back, wanting to restore it. That's why we call it a restorative force, because the force is wanting to bring it back to equilibrium. But it ends up like pulling it too far, and now it brings it back this other negative distance, okay? But then again, there's now a force of the spring pushing it, and it wants to push it back to equilibrium to restore it to what it originally was. And so the point is that it never really like gets there, and so it keeps kind of going too far, too short, too far, too short, and then it has a plus x and a minus x, but the force is always opposite direction of where you stretch it. So Robert Hooke discovered this, that it was a very linear relationship between distance and force, and that it was negative. And so this is called Hooke's law. So the force of a spring in newtons is the spring constant. So every spring has a different spring constant. It's kind of like a fingerprint for an individual spring. And so we're going to measure this in a lab on Monday and Tuesday. And so the spring constant is in newtons per meters, and then displacement, x, is in meters. And notice that there's a negative sign, which tells you that wherever this displacement is, if you push it in, the force is going to be opposite of wherever you're stretching it. That's all that negative means, is that x and f are going to be in different directions. Okay, so our second application of simple harmonic motion is a pendulum. And so in a very similar situation, you have a restorative force that's trying to keep it and bring it back to where it originally started. And where it originally started was right here, and this would be equilibrium. So equilibrium is straight down, okay? And so the restorative force is attempting to bring it back to equilibrium. But in real life, it does succeed because of friction. But in this imaginary world where there is no friction, this is never going to succeed to bringing it back to equilibrium. And really, if you think about it, the main force that is causing this restorative force is just gravity. Gravity is wanting to pull it back down, but because of the conservation of energy, it never does, and it keeps going. Okay, so if you want the maximum displacement, just like a spring, that would be the amplitude or the farthest point away that it gets from equilibrium, which would be right here. So notice that it always returns to the same maximum displacement, and that's another example of conservation of energy, that it always returns to the same point. The energy is always staying constant. And so maximum displacement we measure with this angle. So for pendulums, we measure displacement with angles instead of distance because it's a lot easier. You may not believe me that angles are a lot easier than distance, but trust me, it is. And so another fun thing is that if the angle on this side is theta, then the other angle on the other side is also theta. Just kind of like a spring has plus x and minus x, and they're equal. A pendulum will swing to the same angle on both sides of the equilibrium point. And there is no equation for pendulums. So like I kind of said, is that in both of these systems are very, very classic examples of conservation of energy, because in both of these, the total energy of the system is always staying constant, and that's why a pendulum returns to the same point. That's why spring will return to the same point if it's ideal. And so if you wanted to graph in both of these situations what the energy is doing, you would notice that this blue line is potential. So you start with a lot of potential, like you stretch a spring or you pull up the pendulum, and then as you let go, all the potential drops and then rises and then drops and then rises and drops. And while that's happening, the kinetic energy starts from zero because it's not moving, but then as the potential energy drops, the kinetic energy all of a sudden shoots up. And so if you think about it, like notice how the pendulum stops at each of the maximums, and notice how the spring stops very briefly at each of the maximum displacements. So that means that each of these times that kinetic energy, this purple graph, hits zero, that would be a maximum displacement. And each time that the potential energy hits zero would be when the pendulum is at the bottom. And notice that when the pendulum is at the bottom, it's moving the fastest. So that's why when the potential energy, this blue line, hits zero, the kinetic energy is at its highest. And if you add up the red line, or the purple line, and the blue line, you just get the solid black line, which is the total energy. So notice that the total energy stays constant, it never changes, which is why we say the energy is conserved in both of these situations. So you might be thinking, you're starting the wave unit, what on earth is this going to have to do with waves? Well, if you look at this little graph, and it's going to be a challenge to draw, so don't worry about drawing it. You have this equilibrium point, and the spring is going up and down and up and down and up and down. And if you plot that over time, you end up getting a sine wave, which is so fun. And so what this is going to mean is that if we that springs are an example of sinusoidal motion, but also when we talk about like something in a water wave, okay, technically they don't move at all horizontally. All they're really doing in the water is just bobbing up and down from the water waves. And so this is going to be an important kind of stepping stone for us starting to talk about waves, because you can see that it makes a little wave. So that is the end. And you may be disappointed that we didn't talk about Miley, but we will definitely continue this conversation in class and answer the question why Miley Cyrus doesn't matter.